Okay, so it should be recording now. And I'm going to open up the whiteboard. Right, we should be good, right? Okay, so let's read through the problem and think about it. And maybe you guys, you've seen how I approach it. So, all right, so number 2, a model for predicting temperature and pressure inside an industrial iron melting oven. Okay. All right, so what we need here is basically the X matrix, the Y vector. What are the samples, the classes, define a set of features, define the dimensions of X and Y, and indicate what they mean. Okay? So what do you think? Who wants to? So we need, remember, we need X and we need Y, right? So you should kind of do something like this, kind of like that. Now, whenever you have a problem, right? You don't start by saying, remember, oh, we're going to use an RNN or a CNN. That's not the way it goes, right? Instead, think of the model as a circle, and then think of the inputs and think of the outputs. Got it? All right, so what are the inputs to this? You can come in. What are the inputs to this? What are the outputs to this? So who wants to give it a shot? Yeah, sir. Going into the furnace, right? Okay, so so let's think you guys, are familiar with US Steel, I'm sure, or iron kind of production. So there's a furnace. The way it works, it's got these things called tuyers that provide like natural gas and stuff, and it burns, right? That's the heat. And then up here, there's like material, coal and iron ore and all that comes in, maybe other chemicals and so on, right? And then obviously the idea is to melt, mix, and then down here they plug stuff, I think, and then the steel comes out into like a little bucket or whatever, and then that gets processed on, right? And it becomes the material to sell. All right, what we want is what? What is the model supposed to predict? Huh? Temperature and pressure, right? So are those inputs or outputs? Outputs, right? So temperature and pressure. All right. So we have two outputs. Now, what do these values look like? What are they exactly? What is temperature? Huh? It's a number, right? So it could be like 1500 Kelvin, or let's say in Celsius, I don't know, 1000 Celsius, right? Fahrenheit, I don't know, 600, right? So it doesn't matter. Yeah, it doesn't matter what the values are. You would ask the expert, right? So let's say the temperature is like, 1500 Fahrenheit, the pressure, I don't know, 300 PSI or whatever. I don't know the units. Okay, so, but it's basically a numeric value, and we have two of them, right? Do you guys see that? Now, in the past, I think the problems that we did, they were, what was one problem we did? We did a classification, and it was what, like true or false, or what was it, the problem that we did in class? A3, no, I think the A320, what was it? Gun, not gun, right? So it was a binary thing. All we needed to predict were discrete values, just two, either gun, not gun. But here, the values that we were predicting could be 1400 Fahrenheit, 1200 Fahrenheit, 1170 Fahrenheit, 1356.33 Fahrenheit. Do you guys see that? So that's not a binary or several classes kind of thing, right? So before, we've done what is called a classification problem. This is not that. This is similar, but it's not that. What is this one called? A regression. So please don't forget this. This is a regression. Now, the beauty of neural networks is that they pretty much work, you just have to make some changes and they go from regression to classification. You see, it's like this beautiful thing that can do both things, and you just like tweak here and there. Okay, and this is one of the things that we will play with. So actually, the very first neural networks that we will build are going to be regression models. Okay, so that's actually where I'm going to start. And it's really because it's really intuitive, you know, and it's got a lot of the elements. And then once you understand that, you're really on your way, right? So you've got like 50% of all the other algorithms, and then you start, you know, they just start changing, you know. Obviously, some get pretty complex, like transformers. All right, so we've established that we have two outputs. So then let's start thinking about the dimensions of X and Y, and then we can come back to the inputs here. So what do you think are the dimensions of X and Y? And in particular, what's a row? And then remember, what was the definition of a row in X? We gave that a word, right? What was a row? A sample. Usually we want to think of rows as samples, right? So what is a sample here? This is not like a picture where we had gun, no gun, right? This is a little bit different. So what's a sample here? This one's a little bit more complex.
Each run, you put in
a run.
Yeah.
A run of what?
Like melting this thing and then getting the output.
So what would, okay, yeah. Yeah, go ahead. No, yeah. So yeah, no, that's good, right? So what's a sample? Give me, how do you define a sample? This one's a little bit more tricky.
Completed process.
Completed process. Okay, so time is probably a factor here, right? What would be the time, do you think? Huh? Time, yeah, right. So let's say 24 hours. How about that? Why? How do you make that decision? You need to talk to the experts in the furnace, right? And also they want the models, so they'll tell you what they want. Do you guys see how that works? So a sample could be in an hour, it could be in 12 hours, it could be 24 hours, it could be a run of, these things are pretty slow. I mean, it could be a week, right? Because, you know, they're huge, right? So, but see, this is a nice example in that sense because the sample is not so clear anymore, like with a picture. Picture is super clear. This one's a little bit more tricky. It is whatever you want it to be. But let's just say 24 hours, right? So that's one day. And so what happens in that day, let's say, just to keep things simple, at the beginning, they start throwing in all the material, all the fuels, and turn on the furnace, right? And then the process begins, and then you let it over time, and then at the end of the 24 hours, that's when you want to know what the temperature and the pressure are. Does that make sense? So then obviously you have some sensors, I would say, in the furnace somehow, and you're going to collect that information 24 hours after you start the process. Does that make sense? And you need to be pretty consistent with that. And as long as you're consistent with that, you can compare apples to apples, right? Because every sample, on average, will meet about the same conditions. Do you guys understand? Right? Remember, machine learning is a lot about correlation. What are you correlating? You're correlating whatever you decide this to be to whatever you decide this to be. And as long as it's consistent, the system can predict. Any questions about that? Nope. All right. So then sample we've defined is 24 hours. So that's good to make a note to yourself, you know, and then you say the outputs are after 24 hours. And then you're going to collect information over that 24 hours, right? So then you have to think, now, is it very clear here what the features are? It's not like an image, right? We just grab an image. I mean, you could have a camera that takes a picture of the furnace. I mean, that's an approach, but we're not going to take that approach. Instead, we're just going to do feature engineering, which basically means you're going to use the variables that you think would be good. This is where you might collect 30 features. This is a pretty expensive thing to do because it's a furnace and everything. And then later in the semester, we're going to learn how to do something called feature ranking, which would allow us to know out of the 30 features that we collected, only like 10 were important. And that's good because then we could save money going forward, not using and having to collect the other ones. You know, not buying some sensor that actually doesn't provide any useful information. Do you see that? And that's pretty straightforward. When we look at a tool called Weka, we'll take a look at it there. And then, you know, there's other ways of doing it. Got it? All right, good. So then how many samples? Let's say we've defined a sample, but then how many samples would we have? How do you justify that? Remember, we said it's 24 hours, right? So if a sample is 24 hours, how long do you think you will be collecting data? 3 months? Does that sound like enough data?
100 samples, 3 months.
100 samples is 3 months? So do you think that's enough data?
That's not probably good enough, but it's probably good to start with, enough to start with.
Yeah,
but not
good enough to start with. Actually, I've done some work on a furnace and we ended up with 1,000 samples and simulated data. So it's not a lot. These are the kinds of things where it's not a lot, but also it's easier, right, than finding a gun in a picture, right? It's a simpler process because people really know intuitively what the features are, etc. So let's say, what, 100? I mean, 100 is still okay. I mean, it's still a good number to start, as you said, and it might turn out that it's pretty good. And then you decide, okay, we're going to do another 3 months, and so on. Got it? All right. So we've defined this. So what is this one here? The value of y?
temperature and,
Well, okay. So the number of rows and columns I meant. So what? How many rows in y?
100.
100, right? Exactly, because they need to match perfectly, right? How many columns in y? 2, right? So we can have more than one column, right? So that's perfectly fine. So I'm just going to call these y1, y2. Now I will do this very soon when we look at this problem. I just need to find a nice data set. We can build neural networks that output both y1 and y2 at the same time, and those are called multi-output regression models. Or we could build models that only predict one output at a time. And those would be single output models. Okay. So the advantage of using one model, of generating 2 at a time is that we only need one model, right? And then the other approach, when we do single output, then we would have to build 2 separate models. So if you're deploying them, it's like and then another one. And I think I have found that single models are a little bit better. So, and that kind of makes sense because when you have multi-output, to improve one, the other one has to lose a little bit, and then eventually they find a balance, but they're losing a little bit of precision. Okay. So, and actually I'm hoping to find a data set that has multiple outputs so that you guys can see that effect as well. Okay. What I like about these is that like very small, right? So if we have a data set that's 1,000 with, 8 outputs and 20 inputs, it's a tiny data set that we can really, understand. And then therefore it's, it's easier to visualize basically. All right, so we've identified, now what do these values look like? Just, we have a sample 1, sample 2. What do these values look like here? Their temperature and pressure, right? So they would be what? Let's say 1,400 and 250, 1,150. Now, if you notice, there's something interesting here. One value, the y1, the temperature, basically, if you looked at the range, would be something like that. Whereas the other one, the range might be something like that. Do you see? One is much shorter than the other. Okay, so this is a problem sometimes in machine learning, but there's a very simple solution to this. Anyone know the name of that solution? Normalization. And there are 2 approaches to normalization. One is normalization, the other one is standardization. So basically there's scaling, and then we'll look at both. You can scale actually inputs and outputs. So we can scale and descale, and basically the idea is that machine learning algorithms learn better when the term is normalized. Got it? All right, so we'll learn how to do that as well. But this is really important. So this is one quick way that your models may do really well, okay? Just to do this, and it's not difficult. Got it? All right, so now we've got, so what's the dimension for this one? 2, right? So that's 2. So this is 100 by 2. And then what about this one? This is 100 by what?
Depending on how many,
The-
features.
How many features, right? So how many do we need to have? Why 30? Why 30? Just because you want 30, right? Right. So yeah, I mean, probably not more than 30, actually, because they're challenging to collect, right? So what are these things going to be? Well, they could be the amount of this material going in, right? The amount of ore going in probably has something to do with temperature and pressure. The amount of whatever this fuel is, whether it's, natural gas or could be oil or gasoline or whatever it is, right? Also, whatever chemicals you put in here, the composition of them, etc.
You also
Yeah.
need oxygen.
Oxygen, there we go. So maybe, the quantity of oxygen. You guys, so then basically we're saying how much oxygen went in, how much hydrogen maybe, how much natural gas, how much iron ore, and other chemicals. Got it? And then you have to just measure that, So you say, well, over a period of 24 hours, we're going to inject this much on average, maybe, and they're all averages. So that's fine as long as they're all consistent. Okay. Does that make sense? So I'm not really like too focused on you knowing this, obviously, right? You wouldn't know, just make up some features and these kinds of problems, but something within reason, and then just kind of indicate the quantity. So as you saw, I said probably less than 10, right? So let's go with 10. Why not? Oh yeah, go ahead.
Is it fair to say that, it would be actually a disadvantage to have too many features and not when you don't have enough samples? Because then the dimensionality of the data would, because of the too many features, will
Yeah.
actually make it overfit, more likely to overfit.
Yeah,
Because you don't have enough samples.
right. I see what you're saying. Like you have more columns than rows.
Yeah.
For this kind of problem, I mean, it would be very expensive to get, unless you'd like take pictures of things and use all the pixels, right? But you're right. I mean, I agree with you. A couple of things you can do is, like I said, do the feature ranking and just find out. You can easily find out which features are useful and which ones aren't. And sometimes they have like 0 contribution, so you can just completely get rid of them. And that's a very valuable thing to do.
Right, you mentioned Weka is the tool to do that.
And that's one of the tools we'll learn in this class. It's like a super easy tool that within an hour you're an expert on it. So.
Yeah. What about PCA? Is that?
Well, principal component analysis is a little bit different because principal component analysis transforms features into other features.
Oh, I see. So,
Whereas feature ranking leaves the features as they are. It just ranks them, tells you which ones are useful, which ones aren't, and then you get rid of the ones that you don't want.
because PCA also involves the ranking first, and then you can.
Well, PCA, principal component analysis, singular value decomposition, there are 2 techniques that transform features. So
Right.
they give you new features. Like
Right.
I have 10 here.
There's a composition of the.
It's a linear combination. So like I would end up with PCA1, PCA2, and PCA3, which are weighted linear sums of F1, F2, F10.
Right.
So basically, yes, you have fewer now, but you don't need to do that first.
Sure.
Just use feature ranking first, actually, because from a physics point of view, it's interesting to know what's useful and what isn't.
Right. No, because the reason why I mentioned
Yeah.
it is that whenever I run the PCA in R, it gives you the ranking first. It'll
Okay.
show you how much a feature is
But
contributing.
you're talking about the original feature.
Yeah, exactly.
Well, I mean, I'm sure it's probably that, yeah, it's giving you that, but there's several methods, right? Information gain, chi-square. And so the point is that when you use PCA, you're transforming, you don't know anymore
Right.
what the
end
features
product-
mean.
Right, the end product is a composition
yeah,
or a
Yeah,
combination.
so it might create a semantic new feature, but you just don't know what it is.
Right.
Because it's just called PCA1, PCA2.
Right, sure.
Whereas with feature ranking, you do keep the original ones, and it's just, I mean, you try everything. That's what, data science is, right? So and Weka has all those tools. Yes, sir.
For problems like these,
Yeah.
We also work looking into research that was done in the past before you got machine learning.
Oh, absolutely. Absolutely. That's what I would always do. So right now, I'm just, if you're, I would start here. Because even just starting here then helps you to do research, right? It helps you to think of, okay, that, this is probably a problem with very few features, not that much data. It's regression. Just that alone tells me like a ton of information. And then after that, yes, go on Google and say, start with this actual problem. So you could say something like, what is this? Steel furnace, blast furnace, machine learning. You see that? And then you start there, and then predicting temperature and pressure in ovens and machine learning, right? And then, yes, you start reading papers. But remember, reading papers is a lot of work. And so you start here. You also look at the data that you have, because they may provide you data, and then that influences quite a bit of what you're going to do.
But also kind of
Yeah.
Statistical analysis.
Yeah.
You can find like this thing is significant. What we can predict.
The feature, you mean?
Yeah. Well, like just looking for features to use in this problem in general.
You mean like knowing that if I know that, okay, the natural gas, this specific natural gas will totally tell me what the temperature is. Is that what you mean?
Yeah.
Yeah, that's actually, that's the whole point of feature ranking. So feature ranking will take all the features given this data set, and they will say, feature 3, natural gas, way more important than anything else. Actually, before you do all that, you can also do what is called a correlation coefficients. And we will do that in a few, as soon as we start looking at some data where you actually don't even look at machine learning. You just look at the variables and the correlation between the inputs and the outputs. So that's totally independent of, let's say we're using a neural network, because that uses another set of techniques to just look at how important one thing is. It's a very nice little table, and it tells you, okay, boom, this natural gas and temperature, they have a correlation of 0.6 or 0.9, positive or negative. And then okay, it's got an inverse effect or a linear effect, and so on. Does that make sense?
Yeah, there's one more.
Yeah, go ahead, please.
Like if you kind of find your own research, like these things are significant. How do you go about like assigning weights to the features in that?
The importance?
Yeah.
So there's algorithms for that. So the correlation coefficient goes from -1 to +1. So if there's a zero correlation, I mean, one is not influencing the other. But if one is at -1 or +1, that's really important, because it tells you the effect of one to the other one, whether it's inverse or not. You see that? So there's several techniques like feature ranking, right? Correlation coefficients. We'll look at, and I actually, when I do this kind of analysis, I always start with correlation coefficient. Okay, and then we can do the feature ranking. There's several methods to do that. And then, like I said, PCA and those things, that's a little bit different. Like what I'm really, I want to transform the features and use. Any other questions? Yeah, so we'll do that when we have a data set. I guess I can show you guys, since you have this question, just to give you an idea.
Was that the Pearson test you're talking about, the correlation coefficient?
Yeah, I'll show you.
The Pearson test.
Right, so if we go to, I guess I need to share this. Yeah, so that it shows on the video, I think, right? This should show, I believe. Wait, hold on. All right, let me stop sharing. Share. So basically everything that I'm talking about is something that we're gonna do in a couple of weeks. Or yeah, well, I'm gonna do it with the other class next week. So if we go here. Probably here. Yeah, so this is actually literally the steel. US Steel. So you can see. Right, so you can see we have a model here, right? And some of the data, and then there you go. That's what I'm talking about when I say a correlation coefficient matrix. You can see it's comparing one output, something called raceway flame temperature, to the inputs, which are hydrogen, coal injection, natural gas, oxygen, and so on. So here we can see, if we look at this closely, like this one, natural gas has a very high but negative correlation to the output. Do you see that? So that tells you immediately, and this does not, this is just like standard statistical methods. And then after that, I didn't do, well, with this, I know a lot of information about the features. This is the neural networks that we will look at. We will measure the performance of the neural nets. I'll show you a few techniques. And then I do think I did feature ranking here somewhere.
You could probably just do a search, right? Feature ranking.
I didn't call it feature ranking.
Oh.
I'm not great at like labeling things.
Anyway.
I used a technique called XGBoost, which I will show you guys. It's pretty easy, pretty complex to understand, pretty easy to use. So that's the best thing. Let's see. Somewhere here. Tell me if you see like a feature rankings somewhere in here. Oh, there it is. Yeah, so you can see it's just pretty standard here. See the feature ranking? So it's saying, if you look at that, which one's the most important? Natural gas injection kgTHM. You see that? Because it's got that value 0.61. 0.61, right? So there's several techniques. I mean, like chi-square information gain and a whole bunch of others. We're not going to look at all of those are algorithms, right? So everything like in machine learning is some algorithm for this or that, okay? But a lot of the time we can just, these are built-in tools, so we can just use them and get a lot of insight as to what's going on. Does this make sense? Someone had this question, right? I don't know who had it. Did I answer your question? Whoever asked this?
Over there.
I think it was you. All right. So anything else? Yeah. So this is what we will do. All right. Like I said, we'll follow this. I just need to find a data set for us to do these problems. Okay. All right. So let's go back. I think I need to share whiteboard. All right. So were we done? Okay. So I think we've looked at 10 variables. So the dimensions are 100 by 10, 100 by 2, correct? And then so the inputs are basically about 10 features per sample. And that should be it, right? So that we answer all the questions. We can go back to Brightspace. All right, so the X matrix, the Y vector, what are the samples? What are the classes? In this case, they were regressions. Define a set of features. I think we defined that. Define the dimensions. I provided that. Yeah, and indicate what they mean. So that gets you to start. And then you start reading papers because you want to see how do you tackle this. So there's linear regression, right? Non-linear regression, which will be neural networks. And there is a regression trees, which is another one. Okay. Questions? We are done with this one. So I'm going to go ahead and stop. I need to stop.